Right. So welcome back. And welcome back to the Lévy-Lieb formulation. And so on two blackboards, we will go from wave function to density. So the energy associated with some wave function we can write as some kinetic energy contribution plus the operator describing electron-electron interaction plus the operator describing interaction with some external potential. And now we can consider the set of all those wave functions that map to some given density, to the same density, yeah? And so we simply can compute this one particle electron density of any wave function, and here we consider all those wave functions which have this identical one particle electron density. And of course there are infinitely many of those. And now we can minimize over the set. As follows. So we define a Lévy-Lieb energy functional of the density as the minimizer over all those wave functions that result in the same density. And those wave functions must fulfill some condition. So psi must be antisymmetric with respect to particle exchange because it's a fermionic wave function, and it should have it should map to this very same density n here. And the energy of wave functions we know how to compute. So we just using the expectation value here with our Hamiltonian above. And I'm not going to write each time this condition of the antisymmetry. And now we can here decompose this into two parts, one that depends on the external potential and one that does not. So in particular, this minimization, it's sufficient if it refers only to those parts that do not depend on the external potential. And the part that does depend on the external potential I can evaluate using only the density. So here we had capital V hat. So this was the operator. And in a molecular system, this operator would be given by the summation over all the electrons and the summation over all the nuclei. And then we have the charge of the nuclei. Sorry, for people in the back, it's very small. We have the charge of the nuclei, capital ZA, and we have in the denominator the distance between any electron and any nuclei. Yeah? So this would be up here, we have the operator, and down here, this is a small v without the hat. So this is not the operator, but it's the corresponding potential. Of course, the potential here would be minus summation over all nuclei. And in the numerator, again, the charge, and in the denominator, the distance between here, our single coordinate r, and the nuclei. All right, and now, importantly, this bracket here, it's sufficient to let the minimization run over only the first two terms, because we minimize over all wave functions that result in the same density, and the last term depends on the density only and not on the wave function. And this first part here this is now independent of the external potential. And it is, in this sense, universal, because it depends, well, because it does not depend on the external potential. And this gets a name of its own. So this would be the Levi-Lieb functional of the density. Okay, and now for some given external potential, the ground state is found by minimizing. This function ELL that we have defined above. So the ground state energy is given by the wave function, or by evaluating the wave function that minimizes the energy. So that's the variational principle that we normally have in the Schrödinger equation. And now we can write this instead as a nested minimization. We minimize over the density, and then we minimize over all antisymmetric wave functions that result in the density. And we can only use legal densities here, so n of r must not be negative, and it must integrate to the correct number of particles. So the integral should be capital N, the number of electrons. Okay, and this minimization over psi we can this minimization over psi we had called before. This here was the Levi-Lieb functional, which depends only on the density. And so this minimization, again, is equivalent to a minimization only over n of this functional f, defined above, plus the energy associated with the external potential. Okay, and so in this line, given the definitions on the previous board, this is where the magic happens. So we're looking for the ground state energy, and I've argued before that the ground state energy is this most fundamental of all quantities. Given that, we can do molecular dynamics, we can compute vibrational spectra, we can compute polarizabilities and such, if we consider its variation when we apply an external field. And here on the left-hand side, we had a minimization over all wave functions. And on the right-hand side, we have a minimization over only all densities. And the wave function, well, it depends on all electrons, and the density only depends on a single spatial coordinate. So this is a really dramatic simplification. Yeah? So this goes from exponential description complexity in the number of electrons to just, a three-dimensional function. No matter how many electrons we have, this is always a 3D function. So from left to right here, we have a dramatic simplification. And this is what is afforded by orbital-free density functional theory. And now what's the hitch? The hitch is that this Levi-Lieb functional, well, we can write it down formally. What we have on the board above is a valid definition, but we cannot write it down as an explicit formula, as a practical computational procedure. Yeah? So on the one hand, we have this dramatic simplification. On the other hand, we have this problem that FLL of n is unknown. Now, that being a juicy problem, some of the brightest minds have, of course, tried to understand the structure of this Levi-Lieb functional. And we can write down plausible contributions. So for example, this looks at all electron-electron interactions, and surely it is plausible to use the classical electrostatic interaction of an electron density with itself as one contribution. But there is also contributions that are called exchange and correlation, which are more complex. But the big unknown really has been this one here. Yeah, so how to compute the kinetic energy as a function of the density only. So the biggest the most important, I'm writing here the biggest missing link. Biggest in numerical terms. So how large it is, this is the kinetic energy. which we would like to express as a functional of the density alone. So for a multi-electron system, it's a bit of a sad state of affairs that if you give me, or any theoretician, a multi-electron density, nobody is able to say in closed form, well, what's the kinetic energy associated with that density? It is possible to study it in limiting cases. So for example, Thomas and Fermi came up with a description that's valid for the homogeneous electron gas. So if we have electrons that experience only a flat potential, then it's possible to derive it in closed form. So then you can say that, I'm writing TF here for Thomas Fermi, the kinetic energy is some constant times the integral of n to the raised to the 5th third of a power dr. That's a nice and simple formula, but a molecule, if you look at the potential in a molecule, it's everything or it's anything but constant. Yeah? So this is a very poor approximation for molecular systems and for materials. And it turns out that if you use this for the kinetic energy, and then you minimize over the density, and then you do gradient descent on the result on the energy functional, you have no chemical bonding. Yeah, so it's, I don't want to say useless, but it's not very good for actual chemical systems. And so this is now the wide open invitation for machine learning, or for any theoretician, but it seems impossible for the human mind with the physics that we know so far to derive a closed form formula. Not saying it's impossible, might come out tomorrow, but Thomas and Fermi tried, and Dirac tried, and Weizsäcker tried, and they were not exactly dumb. Yeah. So the challenge is for machine learning in this case to learn this kinetic energy associated with an electron density. And now the good news is that we can generate arbitrary amounts of training data, because for molecular systems we can use the old school quantum chemistry to find we can use Hartree-Fock or MP2 or any of these classical methods to find the wave function that minimizes the energy of that system. And from that wave function, we can compute the kinetic energy and we can compute the density. And that means we can generate arbitrary amounts of training data where we have some density and some kinetic energy associated with the density. Okay, by the way, I said nobody is able to say what the kinetic energy associated with some density is. Some scaling laws are known. Yeah, so you can think for a moment, if I have two densities, I'm trying to draw some complicated electron density here, And now it doesn't have the cusps, yeah? So it's not the density associated with a molecular system. I'm just trying to draw an arbitrary complicated density. And now I'm trying to draw the same density, but I'm diluting it. Yeah? So I'm making it flatter and wider. And I should have made this a bit lower because the integral needs to remain the same. Let me try again. So it's the very same density, just spread out. Surprisingly hard. Okay. So the integral of this should be the same as the integral of that. And it should really be the same, just diluted or squashed. So which do you think has the higher kinetic energy? So the higher kinetic energy is this one here. And that's what prevents the electrons from just falling into the nucleus. Because if you consider the hydrogen atom, the nucleus is positively charged, the electron is negatively charged, and so according to this external potential, the electron would like to fall into the nucleus. We have only a single electron, so this term doesn't exist. And the only thing that prevents this collapse is the kinetic energy contribution. Yeah, so the more widespread, the lower the kinetic energy, and vice versa. And this ultimately results from the uncertainty relation, because if we compress this further and further, then the location of the electron would be known ever more precisely. And by the Heidelberg uncertainty relation, if the location is known ever more precisely, then the uncertainty in the impulse must grow. And the only way the uncertainty in the impulse can be large is by making the impulse itself large, and or the momentum, sorry, the momentum in English. And this is why, compact densities are associated with high kinetic energies. Yeah, so from this we can extract scaling laws and a very, very qualitative understanding we have. But in molecular systems, these are actually huge terms. Yeah, so the attraction between the electron and the nuclei, that's very strong. This term, to counteract, must also be very large. And so we have big terms that cancel out to very nearly zero. Because if the resulting sum would be either very positive or very negative, we wouldn't have, the world wouldn't look like it does. Yeah, we would either live in a world where everything is a perfect gas, so no chemical bonding, or everything is completely frozen, rock solid, everything is strongly bound, there could not be life. Yeah? So we happen to live in a universe where these huge contributions, very large numbers, cancel out to nearly but not quite zero. And this is why we have life at room temperature. And so a qualitative understanding of how the kinetic energy behaves as a function of density is not enough. We must be able to machine learn this quantity extremely precisely. And that, of course, is a challenge for machine learning, to learn it extremely precisely. All right, now this is all very nice, so these this is all true, but here we always wrote functionals of the density. So the first question, when we now want to come to machine learning and to neural networks and so on, is how do we even represent the density as the input? So, you can take a moment and in your mind go through the neural network architectures that we have seen. So we have seen CNNs, we have seen graph neural networks and so on. But the density here, that's a continuous function in space. How are we even going to represent it? Do you have suggestions? So, so we want this here, neural networks rock. We want this to be some neural network. Yeah? But how do we even, represent this density? Yeah. So you suggest parametrizing this function. That's an excellent suggestion because here we had n of r, a continuous function, and okay, it's easy for me to write a neural network depending on a continuous function, but none of the architectures that we have discussed accept really a continuous function. Yeah. So, but when we parameterize it, when we say that, for example, this n of r is a summation over basis functions. I'm using the notation of some particular paper here. Let's say these are basis functions. And then I need coefficients associated with these basis functions. And if I, okay, equality will be hard, but if I approximate it like so, then if these basis functions are fixed, then I now have a finite, if I have a finite set of basis functions, I will have a finite set of multipliers. These are just scalar multipliers. And then I can have a neural network which depends only on a vector of parameters p. And now we start to feel more at home, because this is, what we have been doing for a whole semester. Yeah, look at neural networks that ingest a vector. That's something we know how to deal with. Now, there's still the question of what do these basis functions look like? So maybe the first set of basis functions that you could, okay, and now we come to this point. Discretizations of the density. And let's discuss different options. So one could be a uniform grid. So this is basically, we would pretend that the density is an image, and we sample the image at pixels. This is something where machine learning wise we feel very much at home, because CNNs and such. Yeah. This turns out to be a poor choice for molecular systems because of these cusps. The density in molecular systems is very strongly peaked around the nuclei, and if the nucleus does not sit precisely on one of these grid points, that will not be a very good representation. So one could have a non-uniform grid. We could use an atomistic quadrature grid. And this is in fact what quantum chemists have been doing for a long time. So if there's one nucleus here, then you have for this nucleus a set of grid points, and there's a whole science about how exactly do you distribute these grid points. You try and make it uniform in the angular direction. You try to make it strongly non-uniform in the radial direction because most of the density resides close to the nucleus. So for one atom, this looks very nicely symmetric. As soon as we get a second atom, it has its own set of grid points. Yeah, and these grids start intersecting each other. So this is possible, but if the aim is to go to huge systems, you will have a lot of grid points. So, but here, we have a point cloud, and we could here use a preferably equivariant graph neural network. So here with CNNs, the advantage is that once I've decided how big my grid is, the number of grid points does not change. Yeah, I have constant dimensionality, and in this 3D grid, I can put more or less atoms in it, but this will be constant dimensionality. Here, the dimensionality really changes with the number of atoms that I have, and I want this permutation equivariance and so on. So graph neural networks would seem a good choice. However, it's a relatively expensive representation. And the sparsest representation that you can invent are probably atomistic basis sets. So here you would, around a given nucleus, have a set of basis functions, typically given by spherical harmonics multiplied with some radial function. So for example, we would have this scalar functions, the L equals 0 type. We would have the L equals 1 type. The third one points out of the plane here. We would have the L equals 2 type and so on. And we would do the same for each atom. All right, and here we can use the kind of architecture that we've been discussing last time. So I'm going to also just write GNN here, but this is surely an invitation to use these tensorial kind of equivariant networks that we've been discussing last time. All right, do you have any questions so far? Yes. So the question was, what about the electron-electron interaction term? And what one usually does is decompose this into a so-called Hartree term. That's the classical electrostatic interaction of the electron density with itself. But that leaves more, but this Hartree term does not capture all of that, because we have further energetic contributions resulting from the indistinguishability of particles and such. And this is summarized into a fudge term, which is called the exchange correlation term. So XC for short. And there are two things to say about that term. On the one hand, it is in absolute magnitude much smaller than the kinetic energy. And on the other hand, relatively good approximations exist for this term. They're not perfect, but they're pretty good. And they are what have been developed for many years in the Kohn-Sham formulation of density functional theory. And there is a whole family here. The ones that only depend on the density are called general gradient approximation. And maybe you've heard in some chemistry lecture about these. So there are functionals like blib or PBE, or more recently scan and many others, and they are pretty good. So one possibility is to leave this as is and learn only that part. The other possibility is to learn the sum of these two. Good question. Any other questions? Yes?
More on a rhetorical question. How far will be the stuff that we discuss here relevant for the exam? So will there be a cut where it's not any more relevant?
No. So the question was about exam. So I can say more about exam maybe at the very end of today. Okay, good. Yeah, so the idea is the following. So, okay, let me use a new header. So the ML formulation of orbital-free density functional theory. The idea is to first learn. I'm now writing very generically a functional of the density, and this we approximate by a functional that, sorry, not a functional, but a function that depends on coefficients that are used to represent the density in the kind of expansion that we've seen on the right-hand side. And once this is learned, the idea is for a given molecular geometry, and okay, this will depend on the coefficients, but it will also depend on the molecular geometry. So here it was sufficient in principle to consider only the density by virtue of the Hohenberg-Kohn theorem. If I now operate in some basis, I also need to say where do the basis functions sit. And here I'm including all this in this letter M. And at test time, the idea is to then use some trial coefficients along with the information about where do the basis functions sit and so on, and to put that in the machine learning model and to get out the energy associated with those coefficients and the gradient of the energy associated with those coefficients. And this information can then be used gradient descent style to produce new coefficients. So I can now start adding iteration indices, and I now get out coefficients at iteration t+1. And this I can iterate until I have found some minimum, and the coefficients found at the minimum I can then use to either obtain the density and extract observables from that, or can plug it into this model again to extract the final energy, in this case the ground state energy. Did that answer the question? Okay, do you have more? All right. Then I will use a few minutes to talk about practical realizations of those ideas. Uh, so my impression is that it usually works on the second attempt. First. Okay. So I start with the early 2023 paper where we used this atomic grid kind of representation, which is dense, as input to an equivariant atomistic neural network, which now has its nodes only the atoms. So here it's sparse, and then it's projected back to the grid that's again dense. And from that, we wanted to take the next step and use these atomistic basis functions. But then in late 2023, a paper came out that was really a huge, huge progress. Yeah, and it's from this group here in China. And so this is Microsoft AI for Science, and it was really a big leap forward for the field. So already what we did in early 2023 in terms of generalizability was a major advance over the previous state of the art, but still we were looking at the tiniest of molecules. Yeah, and this paper that represented huge progress because, as I will show in a moment, this allowed making faithful predictions and density optimization on much, much bigger systems. And okay, so in goes a molecule, and out comes an estimate for the energy and an estimate for the density. This just sketches this process of density optimization. Here is a sketch of the architecture. So it's an atomistic graph neural network. So each atom is represented by its position, by the charge of its nucleus, and then by coefficients that represent the density or the contribution of that atom to the overall density. Which architecture exactly is used doesn't matter so much, and out comes an estimate for the kinetic energy. And down here are very impressive results. So if you train it with up to 15 heavy atoms and you test it with much bigger molecules, then you see that this method, if you compute the error per atom, which is a bit, let's say, favorable towards the method, but still, it extrapolates very well in this chemical space. And if you try and make a direct prediction of molecular properties, so if you don't go the density functional route, but just do standard machine learning from molecular positions to energies, so a machine learned force field, you see that this extrapolation error, or the error grows much bigger as you move away from your training data in chemical space. And okay, the second plot tells a similar story, that the machine learned force field, you need a good match of the training data with the test data for the error to come down. And this method operates much more robustly when moving through chemical space. Yes? Those are machine learning force fields. So no density functional theory involved. It just learns interatomic potentials. Okay, down here is some scaling. That is Constraint DFT. This is the proposed method from these authors. Now, actually, the computational complexity is n to the third of this method. Empirically, they find a nicer number here, but as you would go to more electrons, eventually the n to the third will bite you. And here are some details on the particular architecture. So I mentioned briefly last time this idea of achieving equivariance or invariance by the use of local frames. And here you can see these local frames that rotate along with the molecule. And it took us a year, but by now we have better results than this paper. And one of the things that made it possible is the work by Peter and Gerrit, several factors played a role, but one was that the way those orders did it, they could only pass scalar messages between local frames. And Peter and Gerrit generalized this to the use of, or showed how to send meaningful tensorial messages from one local frame to the other. And I would have liked to discuss it in more detail, but time is running out on me. So I will close by trying and answering the exam questions. Before I do that, let me summarize with a single sentence. So I think molecular machine learning is at a stage where it is going to transform those sciences that look at molecular systems. The two most promising candidates are, on the one hand, machine-learned interatomic potentials. They do very nicely as long as you have a reasonable match between your training distribution and your test distribution. And the most impressive paper in the field right now, you have in the OneNote document from last time, I mentioned this foundational model based on maze that looks really impressive and promising. And the other most promising avenue, I think, is currently to learn the kinetic energy in orbital-free density functional theory. This is, I think, a more physical approach than learning interatomic potentials directly. And I hope that as a consequence, this will generalize better in chemical space. And these experiments shown here support this hypothesis.